Hello there, students and friends. This video is a sequel of my past upload on Young's double slit experiment. This time, I'll be discussing problems involving single slit diffraction. So just sit down, relax, watch and learn. Alright, our first question. You pass laser light of wavelength 645 nanometers through a slit 0.250 millimeters in width and observe the diffraction pattern on a screen a large distance away. On the screen, the centers of the second minima on either side of the central bright fringe are 28.0 millimeters apart. Question letter A, how far away is the screen? Question letter B, what would be the distance between these minima if the wavelength were 525 nanometers? All right. So in our diagram here, all right, uh, the monochromatic light in this problem, we are talking about a laser light whose wavelength is known, right? The lambda is equal to 645 nanometers, right? And then there is a slit through which the light passes through. The width of this slit is given, and we denote that with small letter d. It is equal to 0.250 millimeters. All right. Now, uh, just like in Young's double slit experiment, all right, uh, there will also be patterns of alternating bright, dark, what do you call, bands form on the screen, right? And this is the result, of course, of two waves that overlaps, all right? The bright bands, of course, are the results of the interference uh, of the two wavelets, okay, coming from the single slit, okay, which when combined, the resulting effect is a constructive interference, all right? So, uh, whereas the dark bands represent what we call the destructive interference, all right? But since we're talking about diffraction patterns formed on the screen, all right, uh, we are just what we call interested on describing the dark fringes. Okay, unlike in the Young's double slit experiment, where we were more concerned with the bright fringes. So, in the what you call single slit diffraction, okay, the letters small m in our illustration here will be used to refer to the result of the destructive interference, and we call this the minima. All right. The first dark fringe is labeled as m equals 1. So we call this the first minimum. M equals 2 is called the second minimum. M equals 3 is called the third minimum. Now below the central bright band, all right, the same patterns can also be observed. Okay, M equals -1 means this is the first dark fringe below the central bright band. And the second dark fringe, all right, below the central bright band is labeled as m equals -2. The third is labeled as -3, right? So in this problem, uh, the distance between the centers of two minima, referring to the second minima on either side, all right, meaning from the minimum m equals 2 to a minimum of negative 2, all right, how far apart are these two minima? That is given as 28.0 millimeters. All right, they are 28.0 millimeters apart. But we are interested in describing the distance from a given minimum, all right, either from the positive or from the negative minimum to the very center of a central bright band. So y sub m here refers to the distance from any minimum, all right? It could be m equals 1, it could be m equals 2, or m equals 3, and so on. It could also mean uh, from the minimum negative 1, negative 2, or negative 3, as long as the reference is the center of the central bright band. By the center of the central bright band, sometimes it's usually referred to as the middle of the diffraction pattern, right? So when you say m equals 0, that's exactly referring to the central bright band. Take note, m equals 0 is referring to the central bright band and not, it is not a dark band. It is a uh, bright band. In other words, it is the result of the combination or the constructive interference of two waves, crest overlapping with the same crest of another wave, or, all right, two crests overlapping. We call that the uh, what you call central bright band, whose path difference from the slit, all right, is 0, right, resulting to a very bright band happens to be at the middle of the diffraction pattern. So what we are looking for in letter A, how far away is the screen? We label that as capital L, all right? And likewise, in letter B, we are interested also in knowing the distance between the two minima, all right? Between the two minima, second minima, from the positive m equals 2 to the negative m equals negative 2, but given that the wavelength is 525 nanometers, right? So we'll have the detailed solution in a very short while. For the solution to this question, we use this equation or formula. Y sub m is equal to m multiplied by L times lambda divided by small letter d. All right? So, we have already defined each of these quantities. Y sub m here refers to the distance from the mth dark fringe, okay, to the center of the central bright band. That is y sub m. Small letter m, of course, refers to the uh, minimum or dark fringe, either first, second, third, and so on. Capital L refers to the distance of the screen from the slit. Of course, lambda is the wavelength of the light, and small letter d is the width of the single slit. Now, this formula assumes that, okay, the value of y sub m is much less, okay, much less than compared to the value of L, or the distance of the screen from the slit. This kind of diffraction is known as the Braunhofer diffraction. Okay, take note, this formula, all right, is only applicable when the diffraction we are talking about is that kind of diffraction known as the Braunhofer diffraction. If y sub m is not smaller compared to the value of L, in other words, if the screen is very much closer to the slit, then this formula doesn't apply. It's not valid. That kind of diffraction where the screen and the slit are very close to each other, that is known as Fresnel diffraction. All right. So let it be understood that all the problems that we'll be discussing here are of the type known as Braunhofer diffraction. All right. So once again, we emphasize the meaning of y sub m. It is the distance from the mth dark fringe to the center of the diffraction pattern, meaning the center of the central bright band. All right. The value of m, or the dark fringe, okay, is either positive negative 1 or positive negative 2 or positive negative 3 and so on and so forth. Now, for question letter A, we're asked to find the distance of the screen to the slit. And based on this formula, we just isolate, okay, the quantity L. And that will be equal to the product of D multiplied by y sub n divided by m lambda. Right? So, we substitute, okay, the slit width is 2.50 raised to the negative 4 meter. So all the given quantities have been converted to meters. Y sub m, all right, y sub m earlier identified is equal to 1.40 times 10 to the negative 2 meter. All right, and the value of m specified is m equals 2. All right, for a wavelength of 6.45 raised to the negative 7 meters. So doing our math, we will get this value for the distance L, or how far the screen is from the slit. It is 42.1 centimeters. Moving on to question letter B, we are asked to find the distance between the two minima, all right, the second minima, all right, if the wavelength given is not equal to what we have here, right? So the wavelength for question letter B has been changed to 5.25 times 10 to the negative 7 meters. But we are still talking about the second minima, right? Y sub m is the distance from the second minima to the center of the central bright band, right? So, again substitute, this is the value of L that we just obtained, all right? Converting it to meters already, so 42.1 centimeters is just the same as 4.21 raised to the negative 1 meter. And the lambda or wavelength given is 5.25 raised to the negative 7 meters. Okay, divided by uh, the width of the slit, 2.50 times 10 to the negative 4 meters. We will get the value for y sub m, which is 7.07 times 10 to the negative 4 meters. But since what we are asked is the distance between the two uh, minima, second minima, we just multiply, all right? We just multiply y sub m by 2. And what we get is 1.41 times 10 to the negative 3 meters. All right? That is the answer to our question, because the problem, okay, is referring to the separation distance between the centers of the second minima. All right? From m equals positive 2 to m equals negative 2. Question number 2. Rank the following single-slit diffraction experiments in order of the size of the angle from the center of the diffraction pattern of bright and dark fringe, from largest to smallest. Case number 1, the wavelength lambda is 400 nanometers and the slit width is 0.20 millimeters. Case number 2, lambda is 600 nanometers and the width of the slit is 0.20 millimeters. Case number 3, lambda is 400 nanometers and the slit width is 0.30 millimeters. Case number 4, lambda is 600 nanometers and the width of the slit is 0.30 millimeters. So our solution to this question is to use the relationship between the sine of the angle theta to the wavelength lambda and the slit width d. Alright, we have this equation, sine theta is equal to lambda over d. Alright, lambda, of course, is the wavelength of the given wave, all right? And the angle theta is defined here as that angle that is formed by the horizontal line that connects the slit, all right, to the center of the central bright band, right? And another line that connects the slit, all right, to the first dark fringe or the first minimum. Right? That angle between those two lines is what is represented by angle theta. Right. So, the idea is we will just determine the ratio of lambda over d, okay, because that value of the ratio will also be equal to the sine of the angle theta. Right? The ratio is large, it follows that the value of the sine theta is also large, and therefore the angle is large. So we start with case number 1. All right. The given wavelength is 4.0 times 10 to the negative 7 meters divided by the width of the slit, 2.0 to the negative 4 meters, and the ratio is 2.0 times 10 to the negative 3. Now for case 2, the same formula. Lambda is 6.0 to the negative 7 meter and the value of d is 2.0 raised to the negative 4 meters. So the ratio is 3.0 times 10 to the negative 3. For case 3, lambda is 4.0 to raised to the negative 7 meter and the value of d is 3.0 raised to the negative 4 meters. So the ratio is 1.3 raised to the negative 3. And of course, case number 4, the lambda is 6.0 raised to the negative 7 meter, while the slit width is 3.0 times 10 to the negative 4 meters, and we get the ratio 2.0 times 10 to the negative 3. All right? Then we will rank them, all right, from largest to smallest. So the largest, of course, is that of case number 2. All right? Case number 2, if you're going to determine the angle, all right, the angle theta, it will be the largest, all right, and followed by cases number 1 and number 4. So cases 1 and 4 are tied. Their corresponding angles, given those wavelength and the width of the slit, all right, will produce the same angles, all right, and of course the smallest angle will be that of case number 3, all right. The last question, question number 3. A series of parallel linear water wavefronts are traveling directly towards the shore at 15.0 centimeters per second on an otherwise placid lake. A long concrete barrier that runs parallel to the shore at a distance of 3.20 meters away has a hole in it. You count the wave crest and observe that 75.0 of them pass by each minute, and you also observe that no waves reach the shore at positive or minus 61.3 centimeters from the point directly opposite the hole, but waves do reach the shore everywhere within this distance. Question letter A. How wide is the hole in the barrier? Question letter B. At what other angles do you find no waves hitting the shore? Alright, before we go to our calculations, let's first analyze the situations. Right? So supposing this is the barrier, okay, which has a hole in it. Alright? And let's assume that this point here on the shore, alright, uh, the shore corresponds to the screen if you're talking about diffraction of light. Okay, the diffraction of the water wave fronts, okay, can be likened to that of diffraction of light. Now, how far is the barrier, specifically the hole, all right, from that point? We will label it as the uh, what we call the quantity L, right? In our discussion for diffraction of light, okay, L represents the distance from the screen to the single slit, right? So the hole here can be likened to a single slit, okay, in this barrier, right? So that distance from the slit, all right, to this point here, which corresponds to the center of the central bright fringe, all right, in diffraction of light, all right. There is a certain point on the shore, okay, where which we can call as the central bright fringe, all right, and the distance from that central bright fringe, all right, to the what we call first minimum or m equals 1, all right, which we label as y sub m is also given, which is equal to 0.613 meters. All right. Uh, it's understood that there's also another what we call minimum on this side, all right, to the right of this central bright band, all right, but it is no longer shown in this sketch. We are just interested on one particular minimum, or if we're talking about diffraction of light, no, that represents the uh, first dark fringe, But as far as the situation here, we consider that first dark fringe as a point on the shore where there will be no what we call waves, because the waves will cancel. In other words, there will be destructive interference of the two waves, all right, meeting at this point. So there will be no waves. This part of the shore will not experience uh, wave fronts. And so with the other points, all right, that corresponds to the other, what we call dark fringes, okay, if you're talking about light diffraction. So the problem is for us to determine the size of the hole in the barrier, all right? And also, question letter B, we're asked to find other possible angles, right? When we say angle theta, it actually refers to the angle formed, okay? Supposing there is another, all right, supposing this is the first dark band, all right, and we draw a line from the hole, the barrier, to this point corresponding to positive 1, m equals positive 1. So the angle, all right, the angle that is formed by that line, all right, with the perpendicular line from the shore to the central bright band, or to this point here, that is what we mean by angle theta, all right? So, okay, take note that angle theta is defined as the angle formed by the perpendicular distance from the hole to this point that represents the central bright band, all right? And the line, okay, that actually represents the hypotenuse. If you're going to imagine a right triangle, all right, a right triangle whose hypotenuse is the distance from the hole to this first dark fringe, all right? And that opposite side, represented by y sub m, okay, if you divide that by the hypotenuse, that's exactly equal to the sine of the angle theta, right? So this will be illustrated more in our detailed computation or calculation in a short while. All right, so this is now our solution to this question. We use again the formula y sub m equals the product of m L lambda divided by d. And we're given the data such as ym equals 0.613 meters. Also, we are given the speed of the wave fronts, water wave fronts, 15.0 centimeters per second. And also, the information that 75 waves or wave fronts were observed to pass in front of the observer in a time of 60 seconds. So if we divide that number of waves by the time 60 seconds, we are getting the frequency of the water wavefronts, which is 1.25 hertz or 1.25 per second. So we use the simple formula for determining the wavelength, lambda equals speed divided by the frequency, or 0.150 meters per second. We just uh, converted the speed from cm over second to meter per second. We divide that by the frequency, 1.25 per second, and we will get the lambda, or the wavelength, equals 0.120 meters. All right. We are also given the value for the length L. 3.20 meters, or the distance, all right, between the hole in the barrier, all right, to the point where there will be no, uh, I mean where the point of the shore that corresponds to the middle of the central bright band, all right. This is the point on the shore where um, there will be what we call wave fronts reaching that part of the shore. All right. So the first question, letter A, is for us to determine the size of the hole, and we represent that with the quantity D, or the weight of the slit. All right. Using that formula, ml lambda over ym. So substituting for the value of m, which refers to m equals positive 1, meaning the first dark fringe, and the value of L, 3.20 meters, the wavelength, 0.120 meters, all over the value of ym, 0.613 meters. So doing your math, we will get the value for D, all right? In meters, that's 0.626, but in centimeter, it's 62.6 centimeters. And moving on to question letter B, all right, where we are asked to find other possible angle theta, all right, other possible value of theta where uh, the what you call the spots on the shore will also have no wavefronts reaching them, all right. So it's just actually the same procedure, but we will just choose the value for m, all right. Let m be positive 2, right? That's one possibility. Then next would be let m be equals positive 3, and then let m be equal to positive 4. So those are the different cases that we're going to consider. All right? Using that formula again, sine of the angle theta is equal to m lambda over d. So when we substitute for m equals 2, the same value for lambda, 0.120, that is in meters, divided by the value of the width of the slit, all right, which we determine in question letter A, but already expressed in meter, 0.626. So again, doing our math, all right, we will get the value of the sine of the angle to three significant figures, 0.383, and using the formula for finding the angle theta, arc sine of this value, we will get theta equals 22.5 degrees. So likewise, if we let m be equal to positive 3, all right, and then use the same formula again, we will arrive at the value for the sine of the angle corresponding to 0.575, whose corresponding angle theta is equal to 35.1 degrees. And lastly, for m equals 4, or positive 4, all right, doing the same method and substituting the required quantities, we will arrive at the value for sine theta equal to 0.767, whose angle theta is 50.1 degrees. All right. So these angles, all right, corresponds to what we call, there are certain spots on the shore, all right, where there will be no what we call wave fronts reaching those spots as a result of the cancellation of the waves, meaning destructive interference occurred. That's why those points or spots, all right, will not experience any wave fronts. All right. Uh, that will be all. All right. Thank you very much for your indulgence. Thank you very much for watching. Please follow me in my FB page and please don't forget to subscribe to my YouTube channel.